Okay, good evening. Welcome to the November meeting for Silicon Valley ASIM SIGGRAPH. Tonight we will have an exciting presentation by Chris Careaga, who is a final year PhD student at the Computational Photography Lab at Simon Fraser University. I am Alex Junkirk, Chair of Silicon Valley ASIM SIGGRAPH. Before we get to tonight's presentation, let me tell you about our chapter. Silicon Valley ASIM SIGGRAPH has been meeting at different Silicon Valley companies such as NVIDIA, Apple, Intel, and Google for many years. However, since COVID hit, we have moved to online meetings. This year, we would like to return to in-person meetings and are looking for locations where we can meet. Typically, this requires an employee of the host company to sponsor the meeting. If having Silicon Valley SIGGRAPH at your company sounds interesting to you and you would be willing to help us out, please contact us. Our contact information will be in the next slides. Now let me introduce the officers of our chapter. I am Alex Junkirk, and I'm the chair of the chapter. Brent Simon is vice chair. Carl Anderson is treasurer. Sharon Yang is secretary. Ken Zerkowski is a member at large. And finally, this could be you. We are always looking for more volunteers, and we need help in many chapter activities. So if you like what you see tonight, please consider joining us. Okay. If you want to contact us later, you can find more information about us on our website. We also have a meetup page where many of our where the details of our meetings are posted. To email us, you can use this email address. We also have a YouTube channel where past meetings are recorded. To find this information later, simply go to Google and type in Silicon Valley SIGGRAPH into Google. Now to introduce tonight's speaker, here's Brent. Go ahead, Brent.
Thanks, Alish, for the. Chris Careaga is a final PhD student in the Computational Photography Lab at Simon Fraser University. He's received his master's and bachelor's in computer science from Washington University. His research focused on modeling and estimating illumination in images for physically based editing applications. His work has been recognized by the graphics community in the form of SIGGRAPH Asia Best Paper Honorable Mention Reward, and has been featured in various outlets such as the 2-Minute Paper, PetaPixel, and the SIGGRAPH Technical Papers trailer. Please check out his works at his GitHub. Now, Chris Careaga, please take it away.
Okay, everyone, please welcome Chris Careaga.
Cool, yeah, thank you for the introduction. They said I'm Chris. I'm a 6th and final year PhD student at Simon Fraser, the Computational Photography Lab. So this presentation is going to be about the work I've done throughout my PhD. Since this is a SIGGRAPH chapter, I'll focus on these 4 SIGGRAPH papers that are kind of the story of my PhD. And that's why the title is De-rendering and Re-rendering the World, because it's all about those two things, de-rendering images specifically so far, and then showing all the cool things that we can do in terms of image editing by re-rendering them. So to get into it, the first thing I'll talk about is this first paper, Intrinsic Image Decomposition. Let me make sure my stuff is working. Yes, Intrinsic Image Decomposition via Ordinal Shading. This one was presented at SIGGRAPH 2024 in Denver, I believe. And in this paper, we tackled the task of intrinsic image decomposition, which is a problem that has been studied since the late 1970s, is a very difficult problem. And the goal is to decompose a given input image into albedo, which is basically the illumination of invariant surface colors of all the pixels. So the actual true colors of all the surfaces inside the image, agnostic to any lighting effects, basically. And then the second component is the shading or illumination. So we're basically separating these two things out to say these are the real surface colors of everything without any light on them. And this is all of the contributions from light at all the given pixels. And these two components, when multiplied together, should reproduce the input image. And in order to make the problem actually like possible, when I started my PhD, the assumption everyone was making that was that the shading can be represented as a single grayscale image. And we'll talk about why that's a not a very useful, I guess, limitation to put on things, but it made the problem possible to solve. So that's why here the lighting or shading is kind of unintuitively represented as a grayscale image. But we can still get pretty far even under this model. So these decompositions are actually two results from our paper, basically. And so these are two images, their corresponding albedos and their shading, so you can kind of get an idea of how these components look. And you might be wondering, like, why is this a useful problem to solve? And hopefully this presentation will kind of give the idea of why this matters, because we've been able to solve a ton of cool computer vision and computational photography tasks using these intrinsic components, and I'll talk about some of those later in the presentation. But the pipeline, the sort of four main contributions of this paper that made it possible to go from methods that didn't really work super well for any given image to something that really consistently worked well were the following four things. So the first is how we represent the shading values, that grayscale image. The second thing is something called ordinal shading, which I'll talk about how we learn it's a certain kind of representation of the shading that helps our network sort of model the problem better. And then how we can turn these ordinal shading layers that aren't quite the real shading layer into a real intrinsic decomposition that I explained at the beginning. And then the fourth and final thing is how we are actually able to train our pipeline on some real images, despite it being super difficult typically to get ground truth albedo and shading for real images. So I'll talk first about this inverse shading representation. So if we take a given rendered image, something created by a rendering engine, and in this case it's from a data set called HyperSim, we can actually get the ground truth shading layer. We know all of the light interactions hitting the scene and coming back to the camera. So if we just tried to naively visualize the shading of this image, we get something like this that is dominated by these like specular and shiny effects in the image. So there's this like very long tail distribution of the shading values in an image, which isn't great for training a neural network. It's not a great thing to try to estimate given how skewed the distribution is. So prior work had kind of maybe tried to do things in log space. So maybe if we take the log of the shading, that will be easier to predict for a network or an algorithm. But this still lacks like a defined range. You can see here the values go from -3 to +4. They're better distributed, but this like random range isn't great for training networks. And so what we proposed was to use this mapping, which is 1 over the shading plus 1. Which seems kind of arbitrary, but what I'm actually showing here is 1 minus that equation, because with that little equation, it actually inverts all of the values. Turns out you can just do 1 minus and get the same distribution just flipped around. And the nice thing about this is that it's between 0 and 1. So we've basically taken this long tail distribution and compressed it down to be in the 0-1 range, which is really nice for neural networks. To estimate these values, we can use like a saturating activations function like sigmoid, and it can deal really well with these values. One way to think of it, if people are like, depending on people's expertise, is that we're actually just tone mapping the shading. We kind of understand it now as just taking that original shading layer, tone mapping it, and learning the shading values in that tone mapped space. So that's one way that you could think of it. This helps a lot with these like shiny surfaces. So you can see a lot of things in the image are kind of like more matte or diffuse looking, but some things are very specular and they will have a correspondingly very high shading value. So this helps with with those areas that you see on reflective surfaces. So now we'll talk about this ordinal shading, which is a little bit of a technical part, but I can try to break it down. So if we just take, this is another rendered synthetic image. If we try to train a network just using the ground truth shading with typical loss formulations, we get something like this that is not great because the shading is actually a really hard thing to learn. It's a really difficult quantity to be able to estimate just in one go with a neural network. And so, yeah, we get this result that really is not very sharp, doesn't have any global consistency. And so what we decided to do is not just try to estimate these shading values in one step. What we do instead is just focus on the ordinal relationship between pixels. So basically, all our network needs to care about is, does this pixel have a brighter shading value or a darker shading value than this other pixel? We don't actually care about the absolute values. We're not actually dealing with like real physical units of light or anything like that. We're just saying like, is this one brighter? Did it receive more light or did it receive less light is one way to think about it. Mathematically, what this looks like in our loss formulation is instead of directly supervising the network, this is a lot of math, but instead of directly supervising the network, like compared to the ground truth, we have this f of x that is like a affine function. So we're basically saying the network's predictions are allowed to vary by a scale and a shift away from the ground truth. And so all of these different scale and shifts are perfectly valid solutions, right? So the network doesn't have to estimate the exact shading. It just needs to be within some function of the shading. So you can imagine the solution space for the network is a lot larger. So that's kind of the high level intuition. But in general, it makes the job of the network a lot easier. And we find that from the typical formulation, we can improve the results a lot using our inverse shading and our ordinal shading, like formulation, basically. So this is what our formulation looks like, training for the same amount of time with the same network architecture and all that. It improves the sharpness a ton, and it's a much more consistent result. The problem is with that scale and shift, it's ordinal shading is what I'm referring to it as. It's not an actual shading layer. It's not an actual intrinsic decomposition at this point. And so that's where the next step comes in. We notice some very specific behavior of our network at different resolutions. At low resolutions, if we send our images through the network, we can see they're pretty globally coherent, but they lack like fine-grained details. And similarly, if we send it through at a full resolution, we can get back those fine-grained details, but it's at the cost of global consistency. So this is a very well-documented kind of phenomenon with networks, convolutional neural networks, due to their fixed receptive field size. So yeah, it's kind of a trade-off as you change the resolution. And so what we do is we send both of these estimations, the low and the high resolution estimation, through a network along with the input image in order to estimate a final actual shading layer. This is an ordinal shading. This is the actual shading layer. And what we can do now is just, since it should multiply with the albedo to give the input image, we can divide the predicted shading from the input image to get the implied albedo. So basically this is our whole pipeline. Like it's two networks. We first estimate ordinal shading, which is easier, and then we do like a multi-resolution second network in order to estimate the final decomposition. So yeah, that's our pipeline. But the only thing we have to train it on is a bunch of rendered synthetic data. And so in the next part, I'll talk about how we're able to get some real-world data to supervise our pipeline. Specifically, we use multi-illumination data. And there's a data set that has 25 different illuminations of like 1,000 different static scenes. So here's kind of what that looks like. Let's see if this goes. So we have the same static scene, but we're changing the light. Like these are all different lighting configurations. They're moving a flashlight around in different directions. And what we can do is train our network, our whole pipeline on synthetic data first. And then for each of these images, we can estimate an albedo that will be kind of slightly wrong in its own way, but we get 25 different albedos. And all we do is take the median pixel-wise across all of these albedos. And you can see all these little errors get removed, and we end up with one pretty accurate albedo layer that we can then divide out from all of the images to get the 25 different illumination layers. So this isn't perfect data, it's pseudo ground truth, you could call it, but it does help a tremendous amount in generalizing to in the wild data. So here's an example of something that's not in any of the training data sets. And without the multi-illumination data, our shading looks like this. And with the multi-illumination data, the network does a lot better with actual photorealistic appearance. So that's our entire pipeline and how we trained it. And then I'll go over like a couple of the applications from this paper. So the first of them was like some really rudimentary relighting. This isn't actually like simulating a light in the scene. It's just normal based relighting. So you just need the direction of the surfaces and our albedo, and you can kind of simulate like a pseudo relighting. So this was our initial like, oh, look, here's something you could do, but it's not like a full relighting system quite yet, which I'll talk about later. But we can pull our layers into Photoshop. And if we recolor the albedo, what we end up with is like illumination-aware recoloring. So all the shading effects will stay like on this rug, but we can paint the albedo and have the shadows actually accurately reflect things. And so this is a pretty cool thing, and they can be pulled into like readily pulled into Photoshop with the right blending layers, and things just work. So that's our first paper on intrinsic decomposition. And like I said, there's kind of a lot of limitations in the terms of the formulation, like assuming that the lighting in the scene is grayscale, that it's one color. But we wanted to see how far we could push these decompositions and if we could do any interesting applications with them, which brings me to the second paper, Intrinsic Harmonization for Illumination-Aware Compositing. And this paper is from SIGGRAPH Asia 2023. So instead of trying to tackle the full like scene relighting problem, we decided to focus on a specific, on a specific relighting problem, which is image compositing. So this is the problem of like trying to insert an image fragment or a masked like little foreground object into a background scene. And if you want to do this, you need to harmonize it with the background scene. So the thing you're inserting should match the apparent lighting conditions of the background scene. So in this case, it should be lit by this lamp. It's not by default, and so that's the problem that we solve in this paper. And we actually do it by separately harmonizing the, let's see, does this play? The albedo and the shading in two different operations, and then recombining them to get the kind of reharmonized or relit image fragment in context. So I'll kind of walk through the pipeline for this paper. We start with an image, like a composite image. You can see this chair is just inserted into this background scene, and we have a mask denoting which pixels are the ones that are being composited. And here's kind of the final result that we want to lead up to. We start by doing albedo harmonization. So this is kind of due to the fact that our lighting is grayscale. So we have to kind of mess with the color temperature in the albedo, since our lighting can only represent like changes in the general illumination. It can't actually represent like different RGB lights on the thing. So that's one limitation, but we can kind of skirt around it by harmonizing the albedo, which we do with existing methods. And the second part is a reshading portion of the pipeline, where we use estimated normals in a simple graphics model, like a simple shading model, in order to estimate an initial relighting of the image fragment. And then we run that through a network to estimate a like more photorealistic shading layer from the CGI kind of conditioned input. And so, yeah, in order to do this, we have to do some illumination estimation in order to render this like kind of approximation of the image fragment. We need to estimate the lighting. And this reshading network is trained completely with self-supervision, so I'll go over how we're able to pull that off. But once we do reshade this image fragment, we can just multiply it with our harmonized albedo to get a final kind of relit image fragment that we can replace in the image. So first, in order to understand this pipeline, I'll talk about this Lambertian shading model, or direct shading, or diffuse shading. You could refer to it as a lot of things, but just at a high level, what it does is takes normals, so the orientation of surfaces in the image, and a light that could be represented just as a direction, so the direction the light's coming from. And we can get a shading layer really easy with a little bit of math, basically a dot product between the direction of the thing and the direction of the light. And if they're aligned, the thing is brighter. If they're away, then the thing is darker, right? So this is like a single bounce direct shading, like a really rough approximation of the shading of the scene. But the real shading of the scene has a ton more effects, specularities, and all those sorts of things, and self-shadowing, et cetera, et cetera. The list goes on. But the nice thing about this model is we can estimate normals from an off-the-shelf network, and we can estimate real shading from our prior work on intrinsic decomposition that I talked about. So this kind of gives us an equation to bridge the gap between the geometry of the scene and the shading of the scene, which we can kind of estimate, and maybe we can fill in what is the lighting of the scene just using a bit of math. So that's why we care about this lighting model. So now I'll talk about, now that we kind of know about the Lambertian shading model, I'll talk about how we train this reshading network with self-supervision. So to do this, we use existing semantic segmentation data sets, which give us like masked image fragments, basically. So if we have a mask for where the mug is, in this case, we can just pull that out as like the thing we're compositing. We can estimate the normals of it. And then we can estimate that Lambertian shading under the illumination that we see in this scene, which I'll talk about how we're able to estimate the illumination later. But imagine we can just get this Lambertian shading that approximates the shading of the original image. And we can replace the real shading layer with this like CGI rendered version, which gives us kind of like this ugly composite where the shading isn't quite accurate. Maybe it's lit in the correct direction, but it doesn't look real. It looks synthetic, and that's kind of the point. Because now we can train the network to go from this initial Lambertian like CGI rendered version of the mug back to the original image. So we were basically able to simulate this relighting problem, like this reshading refinement problem, without actually having any like ground truth for it. So this is just from semantic segmentation. Like these are just random sets of images with masks, and we've been able to create supervision by kind of removing the shading and telling the network to reproduce it, basically. So that's one way that you can think about it. But when we rendered that Lambertian shading of the mug there, I kind of skirted around the fact that we estimated the illumination of the scene in order to render that Lambertian shading. So now we'll talk about how can we actually get the general illumination of the scene. So like I said, in our Lambertian shading model, we can know the normals of the background scene. Basically, this is the scene we want to composite the image fragment into. And we want to know the lighting. And so we can kind of initialize a lighting. Like we can say it consists of an ambient like scalar value C and a lighting direction L. And right now it's like the lighting direction is kind of pointing up, but we can randomly initialize it basically. And from these two things, the normals and our random lighting, we could render we can render a Lambertian shading, and we have an estimated shading from our intrinsic decomposition. And so now we have like kind of a model to put everything together where we say, okay, if this is what the lighting direction is, here's how the rendered shading should look. And does that look like the estimated shading from our pipeline? And if it doesn't, then we can take a little step in these with respect to the lighting direction and the ambient lighting amount. And this will kind of, this optimization will carry out, and we'll try to kind of match the Lambertian shading that we render to the estimated shading of the scene. So you can see this was that image of the cone where the light's coming from the right, and we've been able to recover the fact that the lighting direction is coming from the right, and it has this intensity, and this side of the cone should be in shadow. And so this is like a really simple way to get like a super simplified or rudimentary estimation of the illumination in the scene. So now that we know like that the light is coming from the right, from that simple process, that little optimization problem we set up, we can plug in the normals of the thing we want to composite, and we can get that Lambertian shading of like that is our initial estimate of how that thing should be rendered in our background scene. So I'll kind of reiterate here. For a given input image with our thing like composited onto some surface, we estimate the albedo in the shading of the composite. Then we harmonize the albedo. That's just with like an image harmonization network. It's like an existing work that we used. It's a pretty like kind of standard problem in this area. So we harmonize the albedo. And then in order to do the shading, we estimate the normals of the object. We do our lighting estimation that says, hey, the light's coming from the top of the scene, which is true in this case. And we render our Lambertian shading that is these normals lit from the top. So it's like now, since all of these parts of the box and the soap are pointing up, they should receive more light. It's a really super straight, like a super simple way to get the rough CGI rendering. And then we send this through our network to get our reshading of the network of the object basically. So this thing should have like a more photorealistic appearance, and we can now put that into our shading component, recombine it with the albedo, and we get this final result. So you can see here it was before when we just naively composited it into the scene, and now we get something that matches the fact that there's light coming from the lamp and hitting these boxes with the soap on it. That's the whole pipeline. So the cool thing is I was able to incorporate this into like a GUI where you can change the parameters of the lighting, and then you'll see the object actually match that lighting. So here it's lit from the right and it gets lit from the right. You can light it from the top, and you can change the ambient strength and the directional strength. So you can edit this super simple lighting model, and then the network will be able to relight it under that light. So here it is lit from the bottom, etc. And what's cool is our method can kind of like adapt to the image. So you can see these little astronauts, wherever you put them, they respond to the local lighting in the scene. And so they're kind of lit more here and in the shadow here. And this is cool because even though these all receive that same initial Lambertian shading, like the lighting model for this scene is always the same. It thinks the light's coming from kind of the roof, basically. So it's three of the same Lambertian shadings, but our network knows how to operate like in context since it's trained on these masked in the wild images. And so it can kind of decide like, yeah, the light's coming from above, but also this thing's sitting in the shadow or it's sitting in the light. And so it can kind of do more reasoning than just this initial shading that we feed to it. So there's some obvious limitations to our approach. We're only reshading the image fragment in the middle, so we don't have any like shadows hitting the environment, which is a pretty big limitation. But it's still pretty cool that we are able to relight anything given how rudimentary our intrinsic components are. As I talked about before, we make a lot of assumptions about the intrinsic components that don't really match our real world expectations. And so, yeah, it was cool that we were able to relight it all, but this kind of made us want to break from those assumptions of the grayscale shading, which brings us to our next paper, which is colorful diffuse intrinsic image decomposition in the wild. And this one was presented at SIGGRAPH Asia 2024. And so in this paper, going back to our first paper, what you could like notice from the fact that we can only represent that grayscale shading is that in images like this, that maybe the illumination looks like it's just white in general. And so maybe that's a good assumption to just have a single channel shading layer. But if we actually look at the albedo that is implied by our grayscale shading, shown here, we can see that even when things look like they're like white illumination, interreflections and specularities and self-shadowing and all these different lighting effects actually are colorful. And so if we don't represent them in the shading layer, they get kind of baked into the albedo layer and result in these kind of color leakage artifacts in our albedo. You can see the same thing on the floor here where if things are specular, those specularities aren't represented in our grayscale shading, and so they have to go somewhere and they end up in the albedo incorrectly. So in this work, we were able to estimate an albedo without these color leakage artifacts. So this albedo has all of the illumination colors removed from it. And instead, the illumination colors get put into a diffuse shading component. So this is an RGB shading rather than a grayscale shading. And it's only the diffuse shading, so like the Lambertian or matte shading, so things that aren't like I guess the light contributions that aren't shiny or specular or things like that, which means we can put everything else into a specular residual component. So anything that's shiny, like the floor here, this gets put into a third component. So our full decomposition now, instead of just an albedo in a grayscale shading, we can have an albedo without any color leakage, a really clean looking albedo that matches the real colors of the scene. The shading that only shows, like you can see that this is a warmly lit room with bluer light coming from the outside, and you can see that that's reflected in the shading layer. So we're actually doing a much better job representing the real world like lighting interactions. And then anything that's shiny, you can see on the floor, since this is a shiny surface, it's not in the diffuse shading, it's instead in this specular residual layer. So that's our new decomposition model. And I will explain the kind of long pipeline for how we're able to pull off this like much more difficult decomposition. So in the first stage of our pipeline for a given input image, we actually start with our grayscale decomposition from the first paper. So this gives us that grayscale shading that isn't very representative of the real world. And you can see here's our little albedo with all of the colors baked into it incorrectly. And what we start by doing is we estimate just the colors of the shading. So a low resolution chroma component. So this is just the color information without intensity, basically. And we can actually add that to the shading layer and remove those colors from the albedo layer to get like an initial colorful decomposition. But you can see that this is low resolution chroma. And so we have an albedo network that takes this decomposition and estimates an albedo layer that is really smooth and has none of the colors baked into it. And a corresponding shading is just everything else in the image. But now our shading has all the like specular surfaces. They're kind of baked in as weird colors in the shading layer. And so in our final network, our diffuse shading network, we estimate just the diffuse part of the shading, so just the matte contributions of the shading, and everything that's specular gets put into our residual component from here. So that's kind of it's a lot of networks and a lot of parts, but I'll break down each part of why we designed it in this way, starting with our chroma network. So here's our grayscale decomposition again. Our image and our two components, the ones from the first paper. And if we take a close look at the albedo, we can see all of these colors, like I said, baked in the shadows and on the walls and for example, on this pot. But if we look at the luminance, like the grayscale version of this albedo, all those colors fade away and we can see that this pot's actually really smooth and these shadows are pretty smooth too. So what that tells us is all of this information that seems like it's incorrectly in the albedo, it's just color information. So the intensity of our shading is actually really good, but there's a color that is leaked in to the albedo, and so maybe we just need to remove that color. So inspired by this, what we do is we take our grayscale decomposition and we send it through a chroma network at a low resolution. So this goes back to our our low resolution, high resolution issue we had in the first paper. We want this thing to be able to globally reason about the whole image to see that, oh, this is all sort of oranger. There's a light from the top that is more of a cool color. And if the network can only look at a little part of the image at a time, it can't do this kind of reasoning across like this low frequency reasoning across the whole image. So we send the image through small and we estimate a low resolution chroma component. It looks like this. And you can see all of the places that are orange and all the places where the cooler light is coming in the ceiling. You can see these lamps represented in this image as well. And we can upscale this and combine it with our grayscale shading layer in order to get an initial colorful shading. So now this thing is RGB. We use the luminance values from the grayscale shading and the chroma values from that thing that we estimated. And now if we divide this out from the image, so basically remove these shading contributions, we end up with an albedo that looks way better, right? Like you can see all these colors were baked into the albedo from the lamps and the blue light and the warm light. And now this whole wall is a uniform white that us humans can recognize. This whole wall should be white. And so you can see this was already pretty successful in getting like the large scale colors out of the albedo. But we're not quite done getting that nice albedo, because if we take a closer look at the result that we get, due to the fact that that chroma was low resolution, we end up with a lot of little color variations in the albedo where the chroma information isn't high enough resolution to like make that surface smooth. Like we know this guy's pants are all the same color, but the network isn't able to get those details while also reasoning about the global information in the image. So we kind of use the fact that neural networks naturally want to smooth the result. And we know that this whole part on this guy's pants should be smooth. His whole jacket should be a uniform color. The floor should all be a uniform color. And so we instead have the network estimate albedo itself rather than shading, which gives us a much smoother, flat result. And you can see all these little high frequency color details that were in the pants and on the floor, they get smoothed out in our albedo. And this gives us our final albedo layer. But like I said before, at this point, we have a nice albedo, but all of the different types of light that come back to the camera are mixed up in our shading layer. And so we have one last network that estimates just the diffuse contributions of the light. So this is the things that aren't shiny. And it's not perfect, but this network can estimate, as you can see, this vase is pretty shiny in the original image, but it's just the diffuse parts of it. So it's not shiny in here anymore. And if we multiply this diffuse shading by the albedo, we get like a diffuse version of the image. So this is the image without specular effects, basically. And if we subtract this diffuse only image from the original image, we should end up with only the specularities. It's everything that's left. And you can see there is the specularity on the vase, and these weird lights on the window and the shininess of this glass on the table. It all gets put into its own layer. So that's our complete pipeline. It's a ton of networks, but you can kind of see how we slowly built up this decomposition that was before this work was like impossible to even get close to. And in terms of training data, we're able to train all of these networks on a bunch of synthetic data and that multi-illumination data I talked about in the first paper, because they all have annotations for albedo. But for the diffuse shading network, we need extra annotations. We need diffuse shading annotations, which you can only get if you like kind of specifically cater the renderer to output those things, and a lot of tasks don't need that. So we only have one data set where we have that diffuse shading. So this part of the network kind of generalizes the least out of all of them because it's only trained on one indoor data set. But since we built things in such a stepwise manner, this network actually still generalizes pretty well to any random image despite being trained only on indoor data. So here's an example of it working on an outdoor image. This is the diffuse shading. Here's an indoor image of some random things, and you can see it kind of gets the warm color temperature. And this plate is shiny, but only the diffuse part is represented here. Here's another image of a building, and you can see the cooler part in the shadow and the warmer part from the sun is represented in our diffuse shading. So despite being trained on that, single data set, it gets the decomposition from all the networks before it, or the network right before it. And so it does a lot better in terms of generalization than if we tried to just do the whole problem in one task, basically. So here's just going back to those examples I showed before where the colors were baked in. Now we can see our albedo is much nicer. The whole table is white, how we'd expect. That yellow tinge is gone. And the floor here is much more uniform. The specularities have been removed and put into their own proper layer. And here's some results compared to some other works in the area that use diffusion. You can see that our albedo is much truer to the original input image in terms of the content has typical kind of generative artifacts. And here's another one where none of these methods are really trained on people, but our method just stays a lot truer to the original input imagery. Whereas other ones, either they have really bad artifacts because they were only trained on indoor images, or they just have diffusion artifacts where they kind of alter the imagery in some way for things that they didn't see a lot during their kind of fine tuning. And if we compare, our method has about 400 million parameters. Even with all those networks, they're not super big. They're pretty good size, but they're not massive. So it only takes about 3 seconds to run our pipeline, and it's a lot smaller than these diffusion-based methods as well. So I'll quickly go over some of the cool things that we can do with these components. One of them is we can actually just, once we have the colorful shading layer, we can just remove the colors from it and reapply it. And we can do white balancing, so we can kind of neutralize all the colors of the illumination in the scene. And again, we can take our layers into Photoshop easily and use the different blending modes, and we can edit the specularity of these coffee beans, for example, just using existing tools inside of Photoshop. And we can do that same illumination-aware recoloring, but now we can do it with colorful illumination as well. So you can see we can change, this wall has both varying albedo and shading, but by changing the albedo, we can maintain the shading and do accurate recoloring that way. So that was our kind of like, that's our final so far intrinsic decomposition paper, but it unlocked a lot of applications just on its own. And that paper won a best paper honorable mention at SIGGRAPH Asia in Tokyo. So that I was really excited for that paper, and so we wanted to jump into like what can we do with these really interesting and like accurate decompositions that really break down the kind of physical world, which brings us to my most recent paper that I just presented here in Vancouver at SIGGRAPH 2025. So this was physically controllable relighting of photographs. So in this paper, we wanted to tackle the task of like full scene relighting, not just relighting an image fragment. And so the typical setup here is that you have some image and you have your relighting thing, and you have to feed it a representation of the illumination that you want. So you want to change the lighting of this scene, and so you have to kind of denote, here's my target lighting, and the relighter should be able to kind of create a rendition of that same scene, but under this new illumination. So it's a pretty straightforward problem setup, but we have to decide how we want to represent this illumination. So there's a lot of ways to represent illumination, like an environment map or something, but we wanted full physical control over the illumination. And so we decided to take a look at how an artist might try to relight a scene or someone really familiar with VFX. And we took inspiration from existing 3D editing workflows and honestly physical sets, like real world sets as well, where you can place any type of 3D like real light source into the scene at any location. It can be a spotlight or a point light or whatever. So here's an example of like in Blender how easy it is to move a light around. And so we developed a pipeline that is actually able to handle this type of lighting configuration. The user can define any type of light source and any 3D point in our photograph. And we can create a like kind of photorealistic relighting of the scene. So here are some of those results. We can change the lighting environment like an environment map would. We can add explicit point lights in 3D locations. We can add them all over with different RGB values. And we're not even constrained to point lights. We can use any kind of light that is available in like a 3D renderer. So here's a spotlight being shined in this, actually, it's a painting of a church. So yeah, we have full control over the illumination of the scene, including the illuminating environment. Like you can see here, we can change day to night. We can even insert explicit light sources into 3D locations of the scene. And we're able to do all of this without any paired relighting data, which is pretty cool. But before I talk about how we are able to train the pipeline, I will go through just kind of like the inference, the forward pipeline that we carry out in order to do the relighting. So the first step in this is we do our inverse rendering step. This is where it ties into our intrinsic decomposition. And we create kind of a proxy 3D version of the scene that can be imported into any 3D editing program like Blender, where a user can set up their lighting so they can insert virtual lights into the scene at specific locations and point lights and environment maps and whatever they want. And once they're happy with that, we just render it with physically based rendering like a path tracer. And we get this initial kind of ugly CGI rendering of our scene. And then we feed that to a neural rendering network, which estimates a more kind of photorealistic version of the image with that lighting that the user set up. So diving into the first part of this, our inverse rendering stage, the first thing we do is estimate using a monocular geometry estimator called MOGI, a point map of the image basically. So for every pixel, it gets a 3D point in space, and they estimate a focal length estimated like of the camera that we can use to render later. But what we can do is actually triangulate pixels next to each other to create a triangle mesh from this that can be rendered with any with any path tracer basically. So we have now a mesh, a 3D mesh created just from that single image. And the second thing we do is use our prior work, the previous paper I talked about, in order to estimate our intrinsic decomposition. And for now, we'll just use the albedo, combine it with this mesh in order to color all the vertices. And we get a fully 3D renderable like representation of the scene. Here it is rendered in Blender. So now that we have something that we can take into Blender, we have a way for the user to kind of set up the lighting that they want. So this is like how you would set up lighting in Blender or in a real studio in the first place. You can add an environment map, you can move a light around, you can add a spotlight or whatever. And once you're happy with how the lighting is set up, we just render with path tracing and we get this kind of ugly CGI version of the scene, but it has the lighting that we want. There are a few problems though. We don't have the full geometry of the scene because of our monocular estimator. It can't see behind things, and there's going to be holes at big depth discontinuities. And we don't know any of the materials in the scene, so we're assuming that this thing is all just a diffuse mesh. It has no material properties, basically. It's just a default mesh, and so like the water looks really weird, for example. But that brings us to our next stage, is once we've actually rendered this with the user's defined lighting, we do a really low level in painting algorithm. This is just like OpenCV, fill in the holes, um, in order to give something that looks a little bit more like an image to help the network in these areas where there's no mesh information apart from the sky. Then we take this rendition or rendering or PBR rendering, the albedo that we estimated earlier, and a mask that tells us which pixels aren't represented by our mesh, so where the holes in the mesh are. And we send that to our neural renderer, which estimates our final sort of photorealistic version of the relighting. And you can see it can do things like make the lighting look better on the building, fill in the holes, and then like adjust how the water looks, for example, in order to make this look like it wasn't CGI rendered, basically. But the main insight of our paper is actually how we train this network. So to reiterate, the job of this neural renderer, which is a CNN, it's just a neural network, is to go from a CGI rendering of our scene that has the right lighting but looks really synthetic, to a photorealistic version with that same lighting, basically. So it's actually really easy to get examples of photorealistic appearance. It's just normal photographs. They're all over the internet, so we can collect as many of those as we want, but it's not clear how we would get the CGI rendering that corresponds to each of those images, right? It has to be that scene with the proper lighting, but that looks like it was Blender or rendered in Blender, for example. So in order to solve this, we actually set up a differentiable rendering optimization in Mitsuba. And how this works is for a given image that we want to create supervision with, we create our colored mesh representation I talked about before, and we render it from the original camera angle uh, with a constant environment map that we just like initialize. So this is just a environment map that wraps around the 3D scene. And right now it's just gray as an initialization. And then we place point lights in a grid, in a uniform grid, over the mesh, kind of at random locations. And the target of our optimization, we don't want it to be the actual input image because, as I said before, we can't actually represent all these specular effects with our mesh. Our mesh is diffuse. It doesn't have any specular parameters or special material properties. And so we remove the specularity from the image. Again, from our intrinsic decomposition, we can just get rid of specularity, which gives us a better target for our optimization. Then we start taking steps with respect to the lighting position and intensities in the environment map in order to match the image that you see on the right, our original image. So we're trying to reconstruct the lighting parameters that actually created our original image. So you can see these lights move over to the window and to this lamp, and they actually reproduce this lighting configuration that we see in the original image. And so what we've done by solving this optimization problem is created an input for the network that is a CGI rendering of the scene. And now we can use the image as the output. Of course, we don't want to supervise the model on the diffuse image, so we put the specularities back on. But we've created supervision just by removing, again, like in the compositing paper, by removing the shading and reproducing it with a physical model like we did with the Lambertian shading model. We can create supervision for our task, which is basically we have a synthetic kind of CGI rendering of the image, and we have our real world appearance as the ground truth. And so we can train our network. And we do this process for maybe 20,000 raw images that we collected from the internet, just from existing raw image data sets, and that's how we train our network. So I'll go over some results really quick. I'm getting to the end of my time, so I'll kind of go through these quick. We can go from night to day, for example, by changing the illuminating environment, or from day to night, as you saw in the teaser, inserting actual physical light sources into the image. We can remove lights, like turn off lights and just have ambient illumination, or we can turn lights on, making it darker outside, for example. And our network's stable to small changes in the input, so we can create these really cool videos of lights moving around the scene and actually interacting with the 3D geometry, moving behind these pillars. And all of this is just a single image, right? So it's really cool that we can insert lights as if this were a 3D scene, even though all we have is one single observation. We can also do things that aren't point lights, like as I said before, like spotlights, anything that can be uh, rendered with a renderer. Here's me being projected onto the side of a building with a simulated projector screen. And it's really easy to incorporate this pipeline into a user interface. So here you can upload an image, it'll create that mesh representation. Then you can move the environment map around. You can add point lights, change their color, and change their intensity. And then you can hit relight, and you'll see on the very right is uh, the final output of the neural renderer. So here we can add a red backlight, and here's our like initial CGI rendering, and then there's our final relighting. And this is real time. It takes maybe 1 or 2 seconds um, to run our neural renderer, so you can kind of get like iterative feedback as you relight this thing. So those are the 4 papers I'll talk about. Um, yeah, they were all SIGGRAPH papers, and you can kind of see the story as we built up from only being able to represent like very rudimentary lighting in the scene with like super simplified shading models, and then like most recently, after 5 years, being able to completely invert and re-render like light transport and images. I think is really cool how much progress we've been able to make over this short span of time. And so for kind of the next things I'd like to work on is making this work for video, for example. Um, Here's how it looks if we estimate every frame of a video, like estimate the albedo. It's not very temporally consistent. So I think it would be cool to get these kinds of things to work for video, to where we could do video relighting, or we could do temporally consistent recoloring of surfaces and get closer to being able to convert like dynamic imagery into fully 3D renderable representations. I think that's a cool direction to go. So yeah, that concludes everything. This is my group. Shout out to my group at SFU, the Computational Photography Lab. My advisor, Yağız Aksoy, of course. And here is my information. This is my website. You can go to and find my links to my LinkedIn and other things like that. If you want to message me or email me any questions afterwards, after we do the Q&A now, that would be great. But yeah, that's everything.
Great talk, Chris.
Thank you.
We do have some Q&A
Okay.
open, so anybody in the audience who have questions, please feel free to use the chat to ask those questions.
Go ahead,
Oh, hi. Yeah, I love your work. Thank you so much for sharing. I was just wondering, like, if some of the techniques could apply to our human bodies, like, skin and eyes that are anisotropic. Like, for example, you mentioned like the multi-illumination data set earlier. So I wonder if, like, by using different like flash photography, for example, or like some tricks, maybe we could also uncover some of the interesting properties of, like, our human bodies.
Yes, yeah. Hi, Jan. It's good to see you.
Yeah.
I yeah, that's another big direction is humans are really hard in general, right? Like not only our standards of how humans are rendered, like we have a really keen eye, obviously, for if humans look natural or not, but also like the skin properties are so complicated, like subsurface scattering and like you said, anisotropy and stuff like that, that it usually requires like very specialized models. So yeah, the that's the main difficulty is like a lot of this stuff I showed, you notice that like there's not very many humans in any of the results, and that's because it doesn't work super great on people. Like a lot of the relighting stuff, you have to kind of hand tailor it to work on people, and you need specialized capture setups and data. So it would be cool if I could, like, if this work could be extended to work better on people, because then you wouldn't need like a light stage in order to capture them. Because that's another thing, like you said, with multi-illumination data, the biggest issue is having people stay still, of course. Like you can get a ton of illuminations for static scenes freely, but having people stay super still is obviously difficult. And so then you need like something that can take images and flash really fast.
Mhm.
Um, and so light stages are good at that. But like what I've the direction I've enjoyed more, or like have worked on in my PhD more, is less about like well, there's some work with like specialized capture setups, but it's like how can we extract supervision from the data that we do have, like a lot of this self-supervision stuff. So
Mm.
yeah, there are avenues. Maybe you've seen that, like we do have a paper on flash photography, like
Yes.
computational flash photography.
Yeah.
Um, but it's yeah, it has been it, it's like a whole nother world in order to get the really good ground truth data for people.
Mm.
And so yeah, I haven't had a lot of time to work on it, and I've seen people even that use light stages, they don't actually go for like ground truth albedo for a lot
Mm.
of things. What typically is used for like relighting is people call them like a D-lit image or a neutrally lit image, or like a in an OLAT stage they'll take like all of the lights on at once. And so the things will still have like ambient occlusion and wrinkles of the face and stuff like that.
Yeah.
But it doesn't matter, because when you're relighting, you need to render those little effects anyway. So the
Mhm.
results end up looking fine. But people haven't, like, people seem to skirt around the fact that getting the actual ground truth albedo for people, like for humans across their whole, you know, face and skin and like the rest of their body parts, is like actually really difficult, I suppose.
Mm.
And so yeah, that is like its whole own research area. But it would be huge for like the VFX industry, for example, working in that direction, because when you're relighting things like in a video context, most of the time you're relighting an actor in front of a CG scene, or in front of some scene that was captured before. And so what you actually care about most is relighting people.
Mm.
But yeah, that has been a big challenge in my PhD. And so yeah, I don't know, maybe that would be something cool to work on. Yeah, for sure.
Cool. Thank you.
Yeah, thank you. Good question.
Yeah, good question, yeah. Ken, I believe you raised your hand, so feel free to unmute yourself.
Yes, I've got a question about refining the albedo.
Yeah.
So, you start out by getting an initial albedo by low pass filtering, and then when you go from that initial albedo to refine, do you use any other information? Do you use the already extracted diffuse illumination? Do you take
Mm.
account segmenting, or what other kind of information do you use?
This honestly, like so at this stage in the pipeline, what we have is this we already kind of have a decomposition. So we're like 90% of the way there, right? Like we have this this shading layer and this albedo that already looks pretty good, as we can see here. But it's just that the color information of this shading layer is just not high frequency enough, basically, in order to represent these little changes in lighting, right? So like you can see this guy's pants are pretty flat, but this this color is still slightly there, and that's because in the prior like part of the pipeline we only estimated that color information at a smaller resolution. So all of these things are just networks. They just get sent, basically they get this well, I can go to
So it's like a course define uh, iteration or something?
Yeah, it kind of is. So like in the first paper, I talked about the fact that at low resolutions, you get like globally consistent things, right? Like your estimations look really good. They're consistent across the whole image, but they're low frequency, right? Like they're just low resolution. And so then you have to do something in order to account for that low resolution nature of them. And that's why we have these two networks here, is that one of them is kind of reasoning about the whole image and trying to figure out like, oh, there's this big blue light on the wall and an oranger light over here, and I need to estimate these colors in order to kind of neutralize those lights, basically, right? But then what that network can't also do at the same time is say that I need to get these little tiny orange interreflections on the pants out, because that's like, it doesn't have the granularity to do it. And so that's why in this stage, we send that decomposition that is kind of partially done through the network that estimates like a final albedo that is smooth. And this kind of uses the fact that networks want to make smoother estimations than their input. Like it's just a kind of like a shortcoming of neural networks is they're kind of always downsampling a little bit. It's really hard to estimate quantities at the same resolution as your input, basically. And in this case, it's okay because albedo is a smooth quantity for the most part. It's like a low frequency quantity in general, because a lot of the times albedo is sparse and constant for like large regions, right? Like classically, people always talk about them resembling like a Mondrian painting, where it's like things are piecewise constant and they're everything's orange and then it's white and then it's blue, like, and they're flat. And so we try to use that aspect to our advantage, and like it's okay if the network smooths things because that's actually kind of what we want. And at the same time, it can fix any weird issues with the color and like smooth out these reflections and things like that. And so we found that with two networks, we can get a lot better of an albedo layer than if we tried to just do everything at once with one network, essentially. So that's what kind of motivates this. It seems like a lot of networks, but I don't have the figure, but in our paper, we actually trained one network to do the work of all three of these, and we like made it twice the size of all three of these combined. So we used a huge network and tried to solve this whole problem and get this albedo, and it looks way worse. It has no global consistency. It has weird artifacts. Like this stepwise thing, even though it seems a little bit tedious, it actually makes a huge difference in like building up a decomposition that stays consistent. And I think it mostly speaks to the fact that this problem is actually a lot harder than it might seem, like from the get-go, because people have worked on, for example, depth estimation a ton, and we've made a ton of progress in it, but we also have a ton more ground truth for that problem, and you're only estimating that one quantity, and it doesn't have to reconstruct the image and do all these things. It's not as physically based on the appearance as this thing is, and so like intrinsic decomposition is. And so yeah, I think doing this in this kind of like tedious stepwise manner actually makes a big difference in being able to get these decompositions to work at all. Actually, yeah.
Yeah, I agree. I'm definitely much more of a fan of a whole bunch of smaller networks because you have accountability there and understandability.
Yes, yeah.
One of the things that came up in what you're describing is what happens when you have textures. I mean, you've got the brick in the background, but what if that person that you had a herringbone blazer and a paisley shirt and corduroy pants?
Yeah.
Would this just get lost? Or
Yeah, it's funny that you say, like, for example, with corduroy pants, like that all that variation, if they're a solid color, all that variation is actually shading, right? So as long as the albedo is smooth, that high frequency information gets put into the shading, and that will, for the most part, work fine. But like you always have this problem basically is that like there are scenarios where one component is smooth and the other one is high frequency, right? So if you have a blazer that has a high frequency albedo pattern, its shading is mostly smooth. And and vice versa for the corduroy pants, they have the same albedo, but their shading is high frequency. They have like high frequency geometry. And so yeah, that's like that's actually funny that you bring it up because the you kind of like always run into that issue. If you estimate shading, then you miss some of those little details on the corduroy pants. If you estimate albedo, you might blur some of the texture on the shirt. So I think it's not a perfect solution estimating either one. I think you're always making a trade-off in like what you can represent. One way that you can kind of get around it is you can even do things with these networks where if your image is say 1024 by 1024, you can send like scale it up to 1500 by 1500. You didn't add any information, but when you send it through the network and scale back down its estimation, it can actually represent higher frequency information because you spread the information out in the input image. So it's kind of counterintuitive, but it's like just from signal processing point of view, you can do some tricks to get as much granularity as you want by like doing clever scaling like we have here, but you're kind of always paying the price in terms of there is some limit on how big of an image you can send the network before it starts losing consistency across like really far regions, basically. Yeah. Yeah.
Thank you.
Great question, Quinn. Do we have any more questions?
I have a question. Actually, I'm not sure what's that orange object on the left on that image. Is that a light source? Or there was
Yeah.
another one you had like a light source, and it seemed like it had some trouble figuring it. I'm not sure what in your network
Yeah.
deals with that
Mhm.
or it's shining through objects.
Yeah, like a visible light sources, you're saying?
Yes.
Yeah, it's a good question because here, let me try to pull up. Because I have one example. So I guess the answer is it's not very consistent. So here, it's hard to tell if the model thinks this is visible. It's actually kind of like this is like a mesh basically right around this light. And it thinks the diffuse shading around the mesh is like smooth. And so it puts all this light into the specular residual. So this is a thing I didn't mention. It's kind of an implementation detail in a way because it's all dependent on how the data set represents visible light sources. So when the model sees a light, it sometimes puts it into the residual layer and sometimes says it's diffuse. So I don't exactly know the behavior, and it's kind of up to how the data set decided to deal with these visible light sources because in the maybe in the example before it here with this is obviously a visible light source, but the model seems to be fine putting it in the diffuse shading. So it does I mean, it's kind of up for these things are all kind of slightly arbitrarily defined in the first place. These are like buffers from a graphics engine that contribute to the final image, but physically, like they don't have a ton of explicit meaning. Like they're just contributions to the light that finally hits the camera, basically. And so they're kind of up to how you want to define them. But by splitting them up in this way of like diffuse shading and specular effects, we can do interesting edits with them and we can use them in like downstream tasks like the relighting network. It was useful to be able to remove the specularity. So that's like why we make this distinction, but it kind of does feel like it's up to the network to decide what it puts in what layer in terms of these visible light sources. So I think it would be probably ideal to unify the its behavior in the data, basically, that like if you when this kind of things happens, maybe we should put it in its own layer, or maybe it should be in the specular residual, but it always needs to be there. Then you have the question of when you can see out of a window, is that a visible light source? Because in some data sets, when you see out of a window, you're just seeing the environment map out the window, and that counts as a visible light source. So then you get weird things there where you need to mask out. Like a big problem with all of this is that the data that we have is synthetic for the most part. Like the vast majority of it is synthetic. The only way to get like precise ground truth really that is dense is to render it yourself. And so then you have all of these scenarios where you're kind of at mercy to how the data set was rendered. And so yeah, you end up with funny things like this. But for the most part, the components behave in like a reasonable way that you can still do useful things with them. But yeah, that is a astute observation of kind of the weird things that happen with how we define the problem. Yeah.
Thank you.
Mhm.
Oh, Chris, if you do have links to your GitHub or LinkedIn or any websites you want to share, feel free to put them in the chat.
Oh,
Actually, I
yeah.
put them already in the description, the link to the 4 papers, I believe, and your GitHub also.
Okay, great. Yeah, I can.
Sure.
But if there's anything else, feel free to.
Yeah, no, the only thing is, yeah, just my website, but yeah, that is, people should be able to, yeah, to find the right things. Hopefully. Cool.
Do you have anything submitted for SIGGRAPH Asia
I
coming
do
up?
not know. I'm at the end of my PhD, and so I'm kind of focusing. I'm needing to focus on finishing it up. There are some things we're working on, but yeah, I didn't have any timely things for submitting to SIGGRAPH Asia, which is kind of like I think that it will be the first one I've missed. Like I went to SIGGRAPH Asia 2020, went to or like had papers in SIGGRAPH 2023, then the SIGGRAPH after, then the SIGGRAPH Asia after that, and then the SIGGRAPH after that. So it's been like a streak of papers, but so this will be the first one where I haven't had one in, but I'm not complaining because it is a lot of work. Yeah, like writing the paper is a lot of work, but also um, getting everything together to present it at SIGGRAPH is also takes a lot of time, and so I'm okay with just focusing on finishing my PhD and everything. Yeah.
Yeah, I wasn't sure quite to modify what the fine definitions of, you've completed your thesis, but you haven't done the oral or whatever. I don't know where
Yeah.
you are in that
Yeah, there's
final steps.
I have a lot of hoops to jump through. Basically, I've been holding them off until my last year, so now I need to do all of the things. But like this was actually kind of a good exercise in culminating, like putting together like some of the material into one semi-cohesive like narrative. It's not too hard to group my papers together in a consecutive way because they were kind of made in order as we kind of discovered things and got things working. And so they have a nice sequence to them and it's like easier to wrap them into a thesis. So yeah, I'm in the process of stapling everything together and then jumping through the hoops of different oral examinations and things. So yeah, that's all the things I have to do this year. Yeah, this school year.
Are you finishing up this year or like?
Yeah, I'll be done in the idea, yes, is that I'll be done in the spring, yeah.
Oh wow.
So
Good luck with your oral examinations.
yeah, thank you. Thank you.
Okay, if there are no more questions, thanks a lot, Chris, for coming by.
Yeah, thank you so
It was
much
a
for
really
having me.
interesting presentation.
It was cool,
I
yeah.
personally really enjoyed it. Yeah.
Thank you.
Thank you, Chris.
Thank you, Chris.
Cool.
And thank you everyone for joining. Hope to see you guys in the next one.
Mhm. Okay.
Okay.
Bye.
Okay, bye.
Bye.